Here we will use the cofactor expansion of determinants to produce a formula for the inverse matrix. So first, a comment on determinants and invertibility. The following fact we're going to establish that A is invertible, meaning that there is inverse to it. If and only if the determinant is non-zero. And so that gives a meaning to the name. The function, which we call the determinant, determines if the matrix is invertible or not. And of course, if the matrix is invertible, seeing that the determinant has to be non-zero is easy, because let's look at the invertibility equation. That the identity matrix is equal to the product of the matrix and its inverse. And if we look at the determinant of both sides, they will also have to agree. But this side gives us 1 as the answer, and this side we can write as a product. And the product is 1 if and only if factors are non-zero. Actually not just non-zero, but mutually inverse. But in particular, this has to be non-zero, and so we have this implication. In the remaining part of this video, we will argue the opposite direction. We will produce the answer for the inverse, assuming that the determinant is non-zero. And the starting point is a cofactor expansion for the determinant. Written for the ith row, it says that the product of matrix entries in the ith row with their cofactors is the determinant. We could rewrite this equation as saying the product of matrix entries by cofactors divided by the determinant, assuming that it is non-zero, of course, is just 1. And so it looks like, if we call this B, J, I, and think of them as entries of a matrix, then this matrix will look almost like the identity. At least on the diagonal, it will be giving us the right answer. So the equations suggest that the matrix has to look, has to be built out of these numbers, which are cofactors divided by the determinant but placed in the transposed way. So really, it is the cofactor matrix. Let me call it C, matrix of cofactors. It's matrix C transposed, and then all divided by the determinant away. So that is known as a Cramer's rule of the Swiss mathematician Cramer, and that is the way of writing down the matrix entries of the inverse matrix. Of course, this is not totally the condition that these entries form the inverse to A. We also have to check that if we multiply Aij with Bjk and compute what is the matrix entry in the product, but sitting away from the diagonal in the row I and column K, that this entry will have to be 0 as in the identity matrix. But that is, according to our definition of coefficients B's, that is one of the determinant of A and the sum of matrix entries times cofactors which are mismatched, which are taken for different row. And that has to be 0, and luckily for us and for Cramer it is. It is really a cofactor expansion the determinant of a slightly modified matrix A. If we take in matrix A and take the kth row and replace it by ith row, not changing anything at all. So in the original matrix we had row I, and just we take it and we put it in place of row J. That is not an elementary transformation because row J is gone, disappeared without a trace. It just been replaced by row I. So we have the same row in the matrix as a result. This A twiddle will have repeating row, and that means that the determinant must be 0 because, again, I could take elementary transformation of subtraction type and subtract this row from that and create a row of zeros. That will make the determinant 0. And so that is the determinant which is manifestly 0, but then when we take row I and expand it using the cofactor expansions, or row K rather, then it will be just the same expression as in here, because the cofactors will be, the cofactors for entries in row K will be the same as in A. And the matrix entries will be the same because we made them the same as in row I. So we'll have this mismatched cofactor expansion. It is always 0 if K and J are different. And if they're the same, we have the standard cofactor expansion, the ordinary one, which gives us 1 after this scaling. So all in all, we have this formula for the inverse matrix, which is useful. So let's just look at the n equals 2 case, the determinant of 2 by 2 matrix. We know well. Sorry, not the determinant, but the inverse. The determinant is AD minus BC, of course, but the inverse of the 2 by 2 matrix we know well anyway. It is 1 over AD minus BC, but let me now do it using cofactor expansion. So the matrix of cofactors, the C matrix, is really the cofactors are themselves, just to remind, are the sign factors and then determinants of matrices which are called minus, and they're themselves determinants of the original matrix without row I and column J. And so writing down the answer, I could start with first the minus, and then the cofactors, which differ from them by signs, and then the transpose, which is the final procedure to be done. So the minor matrix for this matrix A will be just matrix entries, right? Because we're supposed to compute the determinants of 1 by 1 matrices. So for this entry, the minor will be just what is not in the first row in the first column, so that will be D. For this entry, the minor will be C. For this, it will be B, and for that, it will be A. Then the cofactor matrix has some signs entered. Basically, starting from this corner, going along every row and every column, we have to alternate signs. So that is the result. And finally, the inverse is a transpose of the cofactor matrix. Diagonal entries don't change, but all diagonal entries change places, and that is the final answer, which is, of course, matching with the with the result we got anyway by direct computations. For 3 by 3, this formula for the inverse is still useful. It is useful basically anytime, as long as computations of cofactors are not too laborious. So let's compare two methods of computing inverses for a 3 by 3 matrix. But before, let me make an observation So this characterization of invertibility in terms of determinants and the formula we have as a result gives us a conclusion that to have A invertible for a quadratic matrix, for a square matrix, is the same as to have just one side inverse. Because one side inverse already along this rule, along this computation, will give us non-zero determinant. But okay, now let's look at an example. And imagine some ugly matrix, something like 1, 2, put 0 here, 1, 1, make it -2, and 1, and 1, and 0. So something like that. Then again, I will compute the inverse in these 3 steps. First computing the matrix of minus, then computing the cofactor matrix, and then transposing it and dividing by the determinant. But first, to see that we are going to have the inverse, compute the determinant. The determinant, by just computing by the formula, will have this product, which is product of 3 ones, plus terms, these and these will be 0. So the minus terms, that is 0 again, and then with negative sign 2 and with negative sign -2. So totally in 1 that is non-zero, we should have the inverse. Let's compute it first, minus. We'll have to compute 9 numbers, 1 for each matrix entry. So the minor for 1, take away row 1, and row 1, column 1. What is left? Compute the determinant of. The determinant of this 2 by 2 is 1 plus 2, 3 total. Computing the minor for this entry, taking row 1 out and column 2, and the matrix will be 1, 0, -2, 1, reading as columns, so the determinant is manifestly 1. Now this minor, it's just again this upper triangular matrix, the determinant is 1. Minor for this is the determinant of 2, 0, 1, 1. The answer is 2. And minor for this is 1, 0, 0, 1. It's identity matrix, the determinant is 1. Minor for this is the determinant of matrix 1, 2, 0, 1. It's 1 again. The minor for this is the determinant of that, which is manifestly -4. The minor for this is the determinant of, the minor for this is the determinant of 1, 1, 0, -2. The determinant is -2. Finally, this minor is the determinant of this corner matrix, which is 1 without 2, -1. Now, cofactor matrix. We will have to multiply every second entry by -1, starting from the top left corner. Then this, again, along the column is the same rule, so we'll have -2, +1, -1, -4, +2, the sign will have to change, and -1. Here the sign doesn't change. So these 4 entries effectively change their sign when we pass from the minor matrix to the matrix of minus to the matrix of cofactors. And finally, the inverse is just the transpose, because we're supposed also to divide by the determinant, but in our case here, the determinant is 1. So really, it's just 1/1, the transpose of the cofactor matrix, which will become 3, -1, 1, -2, -4, 1, -1, 2, -1. So we, of course, can check that the answer is correct by multiplying with the original matrix and seeing that we get the identity. We could start by really looking at the product in 1, 1 position. So that row by that column will be 3 minus 2, which is 1. Promising. I will not continue with the rest, but instead I will compare this computation with a computation using elementary transformations, just to see that that is not so bad at all. the cofactor, the Cramer's rule, is not that laborious, not much more at least compared to extended matrix algorithm, according to which we have to double our matrix by attaching the identity matrix to it and then do elementary row transformations to bring this to the identity shape. The first move is row 2 minus row 1, eliminating this entry. So we'll have -1, -2 as a result. The last were not changing. The first were also not changing, and then we'll have -1, 1, 0. And then, yeah, we could start eliminating here by row addition as well. So row 3 plus row 2. And we can, yeah, better not cram it all in one step. So we will have 0, we'll have 0, and then we will have -1. And that will be 1, -1, 1, and 1. And now we could start eliminating upwards, sort of leaving this minus sign still later. So getting that is a row echelon form, getting to reducing it, getting to reduced one, we have to start by eliminating entries above the last pivot. So row 2 minus twice row 3 is the transformation. And taking this twice and subtracting. So we'll have -1 plus 2. We'll have 1 minus 2. We'll have 0 minus 2. And so the final move is to get rid of these two. That is a row transformation of row addition, row 1 plus twice row 2. Yeah, we'll do all the scalings later, because our pivots are not ones yet, but we will deal with it later. So when we take this twice and add, we'll have 3, we'll have -2, and we will have -4. The final move is to scale the second and the third by negative sign, and you could see that the result is just what we get using Cramer's rule, so must be correct.